Concorde crossed the Atlantic in about 3.5 hours. Today, the same trip usually occupies most of a working day. The aircraft worked, passengers loved it, and then the entire service vanished. Why did success produce no successor? Not even a slower, quieter improvement. The first clue appeared before Concorde carried a single paying passenger. Start with what cannot be dismissed. Concorde was not a concept render or a one-off stunt. British Airways and Air France ran scheduled passenger services for 27 years. That achievement was real. NASA's plain language comparison is still startling. London to New York in under 3.5 hours, while a regular airliner took roughly twice as long. Passengers bought time itself. They could leave London after breakfast and reach New York before local clocks had advanced very far. For business travelers, that was a genuine product. But the cabin already revealed the limit. Roughly 100 narrow seats, small windows, and premium service. This was not a faster replacement for the wide-body mass market. Concorde proved that an airline could sell Mach 2. It never proved that many airlines could fill many Mach 2 aircraft across many routes at prices a broad market would pay. That distinction between a brilliant flight and a scalable system explains almost everything that followed. The system began as national ambition. Britain and France signed a treaty in November 1962 to build a civil supersonic airliner together, an industrial alliance difficult for either country to abandon. In that early future, air travel seemed to move in one direction: faster. Jets had replaced propellers. The sound barrier looked like the next commercial threshold, not a permanent boundary. The engineering was extraordinary. A slender delta wing, movable nose for visibility, variable engine intakes, and a flight engineer's station crowded with systems. Speed shaped almost every surface. The French prototype first flew in March 1969. 7 years later, scheduled services began. 20 aircraft were built, but 6 were development machines. 14 became airline service aircraft. Mach 2 imposed a punishing design bargain. Air friction heated the skin. Takeoff demanded reheat. The aircraft had to climb high and stay efficient at a speed ordinary airliners never approached. Its 4 Olympus engines were superb at the mission they were designed for. Yet fuel consumption, noise, and maintenance were not side issues. They were consequences of making that mission possible. This is the hidden friction in many future machines. The feature that creates the wonder also creates the constraint. Concorde's speed and its operating burden came from the same design. That might have been manageable with hundreds of aircraft, many routes, and a global support base. Instead, the market began shrinking while the prototypes were still proving themselves. Concorde is often remembered as a commercial failure discovered after launch. The uncomfortable truth is earlier. Most of its prospective airline market disappeared before scheduled service began. The 1974 parliamentary record preserved the reversal. 76 airline options had once been expected to become firm orders. By then, British Airways and Air France had ordered only 9. Options are not purchases, but the collapse still matters. Airlines that had once watched supersonic travel as an industry-wide next step chose not to commit their fleets and balance sheets. The timing was brutal. The oil shocks transformed fuel from an engineering input into a strategic risk. A fast aircraft that burned heavily suddenly faced a world obsessed with efficiency. At the same moment, wide-body subsonic jets offered airlines the opposite proposition: more passengers, more cargo, more routes, and lower unit costs, without asking regulators to tolerate sonic booms. Parliament's own review named the pressures together: noise and pollution, improved subsonic aircraft, fuel shortage, and fuel price. The market did not reject one flaw, it rejected the package. With only 2 state airlines committed, production scale vanished. Every specialist part, training program, and engineering decision would now be spread across a tiny fleet rather than a global family. Concorde still entered service because governments had invested prestige, money, and treaty obligations that preserved the aircraft. It did not rebuild the commercial ecosystem the aircraft needed. Then came the root problem. Concorde could fly supersonically over open ocean, but the noise reaching people on the ground made routine Mach 2 travel over populated land politically explosive. The sonic boom traveled with the aircraft, not just from the moment it crossed Mach 1. That turned every populated overland route beneath it into a political problem. In 1973, the United States adopted its civil overland supersonic prohibition. Other restrictions and public opposition meant Concorde's full advantage survived mainly where the route crossed water. The physics was visible in the network. A London to New York flight could accelerate over the Atlantic. A long journey dominated by land would force substantial subsonic operation and surrender the product. Concorde was also inefficient when flown subsonically. The same aircraft optimized for thin air, and Mach 2 became a costly conventional jet whenever geography or regulation held it below the barrier. Limited range narrowed choices further. The most valuable corridors were wealthy, long overwater routes with enough time saved to justify a premium. Above all, the North Atlantic. Noise, therefore, did more than annoy communities. It prevented airlines from building the dense network that might have supported more aircraft, cheaper parts, and a second generation. The route restriction and the fleet size problem reinforced each other. Fewer routes meant fewer orders. Fewer orders meant higher support cost per aircraft. Higher cost made still fewer routes viable. By now, the answer is no longer the crash. 24 years before Flight 4590, Concorde had already been confined to a small fleet, flying a small number of exceptional missions. That small system could still look successful. British Airways and Air France sold an elite experience: dedicated check-in, attentive service, champagne, and a speed display that made the invisible achievement legible. Fares were high because time was the product and seats were scarce. Prestige mattered too. Concorde carried celebrities, executives, and national symbolism far beyond its share of airline passengers. A 1981 parliamentary debate captured the paradox. The New York route was projected to earn more than £4 million, yet the overall BA Concorde operation was expected to lose roughly $6 million. One profitable route did not pay for an entire fragile system. BA had 7 aircraft but only 2 principal routes, while maintenance, reserve capacity, and crew requirements kept utilization low. The aircraft's visible complexity also implied invisible support: specialist engineers, hot structures, hydraulic systems, intake controls, tires, brakes, and parts that no large worldwide fleet was consuming. Airlines normally improve economics through repetition. Hundreds of similar aircraft spread development, spares, and training. Concorde had 14 service airframes split between two operators from one generation. That is why a direct successor was so difficult. A manufacturer would need to fund a cleaner, quieter, more efficient design for a market that had bought almost none of the first one. British Airways eventually improved its own Concorde economics, but operating success inside one premium corridor was not evidence that dozens of airlines wanted a new global supersonic fleet. The service survived because prestige, sunk investment, and premium revenue held a delicate balance. It did not have the scale to absorb a major safety shock and a major demand shock together. On July 25, 2000, that safety shock arrived. Air France Flight 4590 crashed shortly after takeoff from Paris Charles de Gaulle, killing everyone aboard and 4 people on the ground. The human loss comes first: 100 passengers, 9 crew members, and 4 people in Gonesse. The accident also destroyed Concorde's most valuable non-technical asset, its exceptional safety image. Investigators did not conclude that the basic idea of supersonic passenger flight had suddenly failed. They traced a runway debris event through the tire, wing tank, fuel fire, and thrust loss. The BEA found a precise chain, a titanium strip shed by a departing DC-10 cut a Concorde tire. Debris and impact damaged the wing tank, releasing fuel that ignited. Regulators grounded the fleet. Engineers then strengthened the system with improved tires, wiring protection, and fuel tank liners. The response was expensive, but it was a real engineering response. The liners reduced the risk of a catastrophic fuel release after tire damage. Concorde returned to passenger service on November 7, 2001. That return matters because it disproves the simple story. The crash grounded the aircraft, but did not mechanically force permanent retirement. Yet the repaired fleet returned to a different world. The market was smaller, confidence was damaged, and the aircraft was older. Engineering could restore airworthiness. It could not restore scale. The modification program also increased cost and complexity in a fleet whose specialist support was already spread over very few airframes. A system with little margin had less margin still. So, Flight 4590 was a turning point, not a complete explanation. It removed trust and money from a program already constrained by routes, fuel, fleet size, and aging support. 2 months after Concorde's return, the wider airline industry was still absorbing the shock of September 11th. Premium international travel, the narrow market Concorde depended on, had weakened sharply. British Airways reported severe traffic and revenue disruption after the attacks. Concorde did not cause that downturn. Its unusual dependence on high-fare business travelers made the downturn especially dangerous. By April 2003, British Airways cited a severe economic downturn, falling revenue, and Airbus's view that technical support was no longer economically viable. Air France described structurally loss-making service. The crucial phrase was technical support. A tiny, aging fleet needs manufacturers and suppliers to maintain expertise, documentation, and parts. Eventually, preserving that capability becomes its own business case. Air France ended passenger flights on 31st May 2003. British Airways followed on 24th October. The dates were close because both operators faced the same shrinking industrial ecosystem. This was not a verdict that Mach 2 had been imaginary. It was a decision that keeping 14 old specialized aircraft alive no longer returned enough revenue to justify the rising effort. On 26 November, GBOAF made the final flight of any Concorde from Heathrow to Filton. The aircraft that had represented tomorrow arrived home without an aircraft behind it. Today, movement means towing a museum aircraft, not boarding a faster future. The successor vanished because no single fix addressed the whole system. A safer Concorde still faced boom rules. A quieter design still needed fuel efficiency, orders, routes, and decades of support. Supersonic passenger travel has not remained untouched. NASA's X-59 is designed to test whether shaped shock waves can turn the disruptive boom into a much quieter ground sound. X-59 first flew in 2025 and passed Mach 1 in June 2026. But it is an experimental research aircraft, not a cabin, airline product or prototype ready for passengers. Boom's XB-1 demonstrator has also flown supersonically, and the company proposes Overture for passenger service. Those flights prove engineering progress, not certification, production scale, or profitable operation. A new aircraft must solve several gates together: acceptable community noise, fuel and emissions, useful range, airline operating cost, enough buyers, and long-term engine and parts support. Regulation may also move. In 2026, the FAA proposed replacing the old blanket approach with a noise-based framework, aiming for final rules in 2027. Proposed is not the same as solved. Concorde's lesson is therefore not that supersonic travel cannot work. It is that speed alone cannot carry the economics, route network, and industrial system wrapped around the aircraft. The idea can return, but only when quiet, efficiency, scale, and support arrive with the speed. Concorde solved the clock. Its successor must solve everything around it.